And thanks everyone for being here today, and especially thanks to the organizer for giving me the opportunity of telling you about our work. As you see from the title and as an announced, I will talk about time domain. And what I mean with this is spectroscopies being done in the time result spectroscopy, so in the time domain, to learn about excitation properties of materials, the electrodynamics of materials. So really looking by using time and perturbative approaches there as a mean to access information which would be otherwise inaccessible. As to the kind of materials, quantum materials, of course, refers to a rather broad topic, and these are systems where we try to understand and exploit quantum mechanical phenomena at the macroscopic scale. Perhaps the most famous is superconductivity, but certainly magnetism and topological properties all fit into this category. The work I'm going to be describing today has been done in the Quantum Matter Institute at UBC, and is also part of a collaborative effort with the Max Planck UBC Tokyo Center for Quantum Materials, which is an initiative that started about almost 10 years ago in 2012, and brings together these three research institutions. Before I go into the spectroscopy and the time domain type spectroscopy, let me tell you a little bit more about the kind of materials that we look at. And in particular, let me emphasize the word quantum. And of course, we are familiar with that even when we talk about a single electron. And I find this experiment, which was done in the Netherlands, particularly fascinating. This is a photoionization microscopy experiment where you can basically look at the nodal structure of the radial wave function for a single electron. So it's a rather complex experiment that goes and probes a property we all know very well. The electronic wave function is quantum in nature, has a nodal structure. You can calculate very accurately for a hydrogen atom, and you can actually measure very accurately for an hydrogen atom. And this is the example shown here. However, things get extremely complicated on the experimental side and on the computational side the moment you start adding a second electron. So if you were to look at a two-electron system, and that's because of the interaction between those electrons. So that complexity is really at the heart of quantum materials properties. So when we look at a typical solid, here an example of graphite, which I will be discussing later in the talk. So single layer of carbon atoms stuck on top of each other. And what you're looking at now is not just a single electron moving in the system, but the physical properties are driven and by those 10 to the 23 electrons you have in the solid. And that is the challenge that we are facing every time we look at materials, and in particular, every time we try to understand a new material. Now, a particularly interesting aspect is that of going beyond the understanding of these properties, but approaching actually the design of new materials. Sorry, a garbage truck is going by here, so let me know if it is too noisy. But the one exciting aspect is that really of designing new materials, so designing new physical properties. And in recent years, many of you may have seen this kind of work. Here I'm showing work that was eventually covered by the New York Times. And initially this work was led and championed by Pablo Rio Herrero from MIT. The idea is to now take graphene, single layer graphene, and stack two of these layers on top of each other and control very accurately the misaligned angle between the two. Here you can see it shown in this the rotation of the two sheets. And if you can control that very accurately, an angle which is about 1.1 to 1.5, this is so-called the magic angle, you can now induce superconductivity in this material, which otherwise would not be a superconductor at all. And so this is really the engineering of materials. And it's actually interesting to see that superconductivity has made, once again, the headlines of major journals and magazines. This, in a way, is reminiscent of what happened back in the 80s, at the end of the 80s, with the discovery of high-temperature superconductivity, which made the cover of Times magazine. Now, this kind of approach has also been inspiring work that we do at the Quantum Matter Institute in UBC. I'm here showing work done by my colleague Marcel Franz, and the idea now is to twist not two layers of graphene, but actually two layers of a high-temperature superconductor. This is shown pictorially here, The material in being studied is a bismuth cuprate. So the building block of this system, which is becoming superconducting at 96 Kelvin, is the square copper oxygen plane. And here you see one copper oxygen plane stacked on top of the second one with a rotation angle, which in this case is 45 degrees or close to 45 degrees. And as you do that, because this system is characterized by what is called a pairing gap or a superconducting order parameter, which has a D wave-like shape, in particular dx squared minus y squared, as you stack two of these systems on top of each other, you have these two order parameters misaligned by 45 degrees. And so where the order parameter was 0 for one system is now maximal for the one below. And if you have a finite interaction between the two layers, you can now induce a new state of matter. And this new state of matter is a topological superconductor, but now a high temperature topological superconductor. And basically, in formal terms, it means that you've now created a new superconductor with an order parameter which is no longer just dx squared minus y squared, but also has an additional complex component. And this is what leads to topological superconductivity. Without going into the details of what topological superconductivity means, let me just tell you that as a signature, this system will break time reversal symmetry similar to what a magnet would do. So it can be probed by optical experiment that look at that. But what is really interesting is that this system will sustain new kind of excitations, so-called Majorana edge modes, which are pretty much considered one of the most promising avenues towards quantum computation, so robust quantum computation, in particular topological quantum computation. And so this work, which really embodies the vision of our institute, QMI Institute, that vision, which is based on quantum materials by design, is one way to go from a pristine system and define new phases of matter, which could be relevant for groundbreaking applications. Now, the first step in this kind of work, in addition to the conceptual idea of designing these phases, is to go and probe these phases. And so the electronic structure is the key here. And we all know that going from, the electronic structure changes dramatically, going from atom to a molecule to a solid. You go from discrete or molecular electronic levels into electronic levels in a solid. And the key element here is not only that you have, instead of discrete level, you have bands of allowed energy and disallowed energy, but you also have momentum and as a new quantum number. So the crystal momentum of an electron propagating inside the solid. And so this is where, the technique I use will come in. And so if you look at the dispersion of electron in a solid, the key energy level is the one which is called the Fermi level that separates the occupied from the unoccupied part of the electronic structure. And there is actually a quantity that really characterizes that in momentum space, which is called the Fermi surface, which really, is a well-defined locus of point in momentum space that characterizes the system, whether being a metal or an insulator. If there is no Fermi surface, the system will be an insulator, and what kind of metal and dimensionality this system would have. To study these effects, the technique is angle resolved PHOTOEMISSION spectroscopy, so-called ARPES, and this is basically what I've done for most of my scientific work, and it goes back to the photoelectric effect explained by Einstein a long time ago, and has now become a very mature tool to study the electronic structure of solid. Photons coming onto a sample, electrons being photoemitted in vacuum, collected by an electron analyzer, which at the end of the process will discriminate the number of electrons as a function of their kinetic energy and emission angle. So what you see here as a color plot are the electrons coming out of the solid. And you can then use conservation laws for energy and momentum to go from the measured kinetic energy in vacuum to the binding energy of the solid. And of course, the two quantities that connect to these two energies are the photon energy and the work function. And from a momentum in vacuum, you can go now to the momentum in the solid. And what you can then do is, map those intensity plots onto the band structure you can calculate using, for instance, density functional theory. Now, in the particular work that we are doing these days, we are doing this kind of technique, but we are doing that in the time domain. And so what it means here, you see a complex system of laser beams, which I will explain in more detail in a moment. But the key point here is we don't only shine a photon onto a sample which would emit electrons, we also shine a second photon, here shown as an infrared photon, which will excite the system under investigation before we go and probe it with the second photon that will remove the electrons. So typically these two photons will have very different energy, with one being into the infrared or to visible, and the other one needing to be a high energy photon, so UV or soft X-ray. Today I will show a little bit about the technique, and also in particular about this work, which has to do with probing electron-phonon coupling, which is one of the fundamental interactions in solids, using this kind of approach. So here is on the technological side, there is a major development which has taken place over the last few years. We have spent basically 10 years doing this work, and that was done with my colleague David Jones at UBC. The two groups have worked together extensively on this, and the key was the development of a laser source that could give you photons in the right photon energy range to be able to do these experiments. And let me explain you what this entails. So the way we've done it, or higher, generation of high energy photons is usually done, or can be done, is using basically conversion of an incoming photon into a high energy photon through a gas jet. So the idea is to generate very intense laser pulses, so very short and very intense, focus them on a gas jet, and through what is basically a partial ionization of the gas. So an electron that is being removed from the gas, when the electric field comes in and deforms the potential of the atom, and is then released when the electric field changes sign and goes back into the atom, a high energy photon can be emitted. So this is how typically the harmonic generation in gas has been done, and it requires very strong amplification of your pulses. It requires, therefore, a low repetition rate type system. It requires, pulses which are very compressing time, very short, which in turns will lead to a very low energy resolution when one wants to do spectroscopy. So the approach that my colleague David Jones has then used was to not just send a pulse into a gas jet individually, but actually take advantage of what is called a passive enhancement cavity. You can see two mirrors, so the seed pulses are now coming into the cavity, and they adapt coherently, so you're storing energy into this cavity, and as a result, you can generate very few photons per pulse, but you can now enhance your repetition rate, send many pulses per second, and as an outcome, you will have many photons per second. And at the same time, a very high repetition rate for your laser source, which will have an advantage, as we will see. So here is a scheme of a system that we have. We have a seed laser, which is going to do, is doing two particular tasks. One is to generate a pump pulse that will go onto a sample facing the analyzer. But the other one, the more critical, is to pump the cavity, the enhancement cavity, the passive enhancement cavity, which is in this case is a 5-meter long cavity with several bounces and a grating which will select the particular harmonics generated into the gas jet that we would like to send to the experiment. And if you see here a picture where the harmonic has been generated in krypton gas or argon gas, you can see many different peaks. And so really the range that we can span in this system goes from about 8 to about 44 electron volts effectively. And you can choose that in steps of the other harmonics of the fundamental. And what is key, of course, is the stability of this cavity is critical and very delicate. And so we need to keep a 5-meter cavity stable over 24 hours during the experiment at the level of 2 nanometers. So that has been the main challenge in developing this system, which has taken about 10 years to get to a point of being effective. Now, if you look at what is available and where the field is going into this kind of work, Here are two examples. On the right, you see our lab at UBC. You see an ARPES chamber, so the photoelectron spectrometer, and you see two laser enclosures on either side. One is working on crystals, so generating 6.2 eV photons, and the other one is the one I just described, so in a gas jet, looking 8 to 40 electron volt photons. On the other side, you see a system in the UK, ARTEMIS, a free electron laser, which now generates also very high energy photon, 10 to 80 electron volts. But of course, the two systems are very, very different in the way they operate, in the way they can be used. The key is time resolution, one versus the other. You're looking at a free electron laser, 30 femtoseconds. In our case, we are approaching 200 femtoseconds of time resolution, and the other one is energy resolution. While 200 MeV is a typical one in this experiment, we are looking at 20 MeV resolution. So really depending on the kind of physics you want to study, you would choose one system versus another. And another key difference is the repetition rate, looking at kilohertz type repetition rate versus megahertz in our system, which basically means high repetition rate, very high signal to noise. At the same time, though, if you want to excite a material and you want to excite it non-perturbatively, you really have to work at kilohertz regimes, both in terms of being able to generate the power you need to do that, but also to allow the system to relax back to its initial state, to equilibrium, before a second pulse comes in. So again, two machines, two very different type physics you can access, non-perturbative, perturbative. As a whole, this field is now expanding very much. For a technique like this one in the past, you would have relied on synchrotron facilities, basically. These days, a lot can be done on laser-based system completely in-house. So here are, the list of references, recent references for high harmonic generation in crystals, and you can see that the photon energy, which is a key parameter limited to 6 or so electron volts, 7 electron volts, that's the range, typical range. Newer development are gas phased and free electron lasers. And here you see that now the photon energy can just go up very much to very high energies that we've seen. And then the two key parameters again are photon energy and temporal and energy resolution. And so here is our system, 25 eV in the particular experiment that is being referred to here, 22 MeV resolution, 60 megahertz, 190. These are the parameters that we're describing. But certainly, if you were to push and go to higher energies, or you can certainly do that. And then you can see, for instance, you can go to 13 femtosecond temporal resolution, 1 kilohertz, and then you lose on the energy. So really, again, that balance between time and energy, which is fundamentally engraved into this kind of approaches. Okay, so now let me come to some physics of what we can study by using these kind of techniques that you cannot access by normal photoelectron spectroscopy, for instance. I've mentioned systems like graphene, superconductivity in graphene. I mentioned high temperature superconductors. And so one key property when it comes to superconductivity, and in fact, not just superconductivity, but also charge density waves in solid, is electron-phonon coupling. So here is an electron propagating into a crystal. The electron is interacting with the lattice deformation that it induces in its motion. And as part of that, that lattice deformation can overcome the natural repulsion between electrons. And so a system can go into a transition, into a superconducting state, where now two electrons form a bound state, the so-called Cooper pair, and the system becomes a superconductor when coherence, macroscopic coherence is established. So electron-phonon coupling and such is one of the fundamental interactions in solids, and many techniques have been developed to study that. One, of course, is theory, so ab initio calculation, density functional theory. But on the experimental side, there is, the situation is a challenge. You can use, on the one hand, scattering experiment, whether it's a particle scattering or photon scattering. And in this case, you're going to learn about the coupling between electrons and phonons for one particular lattice vibration of the system. But this is integrated over all possible electrons in the solid. Other approaches take advantage of angle resolved photoemission spectroscopy by looking, for instance, at what is the typical dispersion. This is work we did in graphene, where we induce superconductivity in graphene by depositing lithium atoms on graphene. And what you see here is energy versus momentum. Graphene should have a Dirac-like dispersion, so a linear, perfectly linear dispersion. And you see that around this energy, there is a deviation from linearity. In a way, you see two different slopes in this plot. And that distortion of dispersion, which is referred to generally as a kink in the dispersion, tells you that there is electron-phonon coupling, which modifies the electronic spectrum down here. And so through a rather detailed analysis of this, you can try to extract what the value of electron-phonon coupling is. However, this is very challenging, relies on a detailed modeling of the data, so it's not so direct, and also tells you the coupling for a particular electronic state, let's say the states over here, integrated over all possible modes of the system. So in a way, it doesn't tell you about a specific one. So the idea was, can we now work in the time domain and extract the electron-phonon coupling for one particular electron to one particular phonon mode of the system? So what is, we basically refer to an electron-phonon coupling which is resolved in the K of the electron and in the Q of the phonon. So here's the idea. We take graphite, but let me, as a benchmark sample, but let me discuss it as, based on the graphene, which is simpler from an electronic point of view. You have your Dirac-like dispersion. The dispersion is, or the electronic structure is occupied below the Dirac point and unoccupied above. But you can come in with a pulse, in our case is a 1.2 eV pulse, and excite electrons from below the chemical potential to above the chemical potential. And then what you can do is you can see how these electrons will relax over time. And so what you're going to see, if electron-phonon coupling is important, you're going to see that the electron will relax by emitting a phonon with a given energy h bar omega. And so you're going to see a transfer of spectral weight after the excitation to discrete levels below the particular state you have excited. And in the simulation, basically what you would see here is, the occupied electronic structure of graphene, and you go and excite above the chemical potential, which would be located right here. And then over time, after a characteristic time pi q, which is the electron-phonon scattering time, you're going to see that part of the intensity trickles down in discrete steps of h bar omega. And if that were the case, you can use a very simple relation which connects the electron-phonon scattering time to what is called the electron-phonon matrix element. So the Q projected electron-phonon matrix element. Or alternatively, you can also express it in terms of the electron-phonon coupling itself. So two ways of looking at it, and all you need is to determine what is the electron-phonon scattering time. So here is how we prepare for an experiment like this, and where the challenges come from. We have graphene, which means if you look at the electronic structure of graphene, you look at the symmetry unit in momentum space for graphene, the Dirac point is located at the zone boundary. So in terms of momentum, is a very large momentum away from the gamma point of the solid, which means that if you were working with 6 eV, you will be confined in photoemitting electrons from close to the gamma point, and you cannot access this particular point. So 25 eV is what we were aiming for in order to be able to probe this particular dispersion. If you look at now at what you're trying to do is looking at electron-phonon interaction. So you're looking at phonon typical energies of the order of 100 millielectron volts. So you need a high energy resolution. And if you look at scattering time, you also need reasonably fast time resolution of the order of 100 femtoseconds. And so that's where then we came in with a system like this, and we built a system aiming at 25 eV, 190 femtosecond, and 20 eV resolution. And the key then is that the repetition rate of 60 megahertz will be very important in order to be able to see very faint features in your spectra. And so here is the system which I described. And so while the cavity generates the UV photons that are coming in at 25 eV, the infrared beam, which is the same that seeds the cavity, is also used to pump our system and generate a hot population of electrons that will relax down. If we now go to the experiment, here is a dispersion where you see the chemical potential, here is energy, and here is momentum. So basically we are looking at this Dirac point here, or Dirac cone, and in blue and red, means that we are not just looking at the spectrum, we're looking at the difference between the spectral measure after the pulses arrive, the pump pulse, and before. So in red, you see enhancement of population above the chemical potential, where before there was no electron at all. And in blue, you see the depletion of population below the chemical potential. So you have excited electron from below to above, and now you see how they relax. What we are after are these features here at higher energies. Unfortunately, if you look here, you see nothing. And the problem is the intensity. The intensity down here is 4 orders of magnitude less than what you have around the chemical potential. So in order to see if something is going on there, instead of looking at an energy momentum map, we integrate the spectra and show a single spectrum as opposed to a 2D map. And if you do this, and you look at a range which is around 0.6 electron volt above the chemical potential, you start seeing, and these are the raw data, on top of a tail, a background tail of scattered electrons, you can see structure. And now this structure can be interpreted, and this is the key fingerprint of electron-phonon coupling we're interested in. So in the analysis, what we do, we remove a background, and we just look at these 3 peaks. And what we can see is that the 2 of these peaks are due to optical excitation that we can generate through the pump probe. But the 3rd peak is not an optical electronization, and in fact is exactly pushed back with respect to this first one, the most intense, by the energy of a particular phonon of the graphite system. So in fact, we can study as a function of delay the full dynamics of these 3 features, and here are the results. So we have the 2 in blue, we have the intensity of these 2 peaks as a function of delay. 0 means the pump and probe are coming coincident, at the same time on the sample. Of course, they have a certain width, so you see that the intensity of those 2 blue features, which we call DTP as a direct transition population, grows until the 2 pulses are coincident and then decays again. And the dynamics of these 2 features is exactly the same, the maximum exactly the same location. The other one, which we call the phonon-induced replica, so PIR, has a dynamic which is quite a bit different, because in fact that feature reaches a maximum almost 50 femtoseconds after the optical transition has been generated. And so these 2 quantities, the energy difference between the 2 peaks and the time difference between the intensity of those peaks, allows us to now go and calculate these quantities, which is the electron-phonon matrix element. It allows us, first of all, to identify this as an electron-phonon effect, and this being a photon-induced replica, but also then extract through the tau q what is the value of GQ and the value of lambda. So if we look at it, we have a measured value of the Q projected matrix element for a particular mode and a particular electron of 0.05 electron volt square, and we can calculate that for graphene since the system is well understood from a theory point of view, and we get a very good agreement between the 2. So in a sense, this has been the most precise measurement of electron-phonon coupling in graphene, and this has been done entirely in the time domain through this very simple relation. Excite an electron, see how it relaxes, and then extract electron-phonon scattering time and directly invert this relation. Now, for the expert, it might be interesting to go and look at this measure value in relation to other techniques. And so here, and I'm not going to go through this in detail, we have taken graphite as a reference because of the fact that we are working at very high photon energy. We're populating states above the chemical potential, and the comparison between the data we extract on graphite and graphene is actually extremely accurate as well. In the last 2 minutes, let me just mention that this technique, now I show one example using time-resolved photoemission to look at one fundamental interaction in solid electron-phonon coupling, but the same approach can be used to, for instance, populate states above the chemical potential, which is what I showed, but not just one, but a multitude of states, and basically compare now, learn about not only the electronic structure, the occupied part, but the unoccupied. Here an example of topological insulator where you have an experiment for the unoccupied part and the calculation for the unoccupied part. Again, beautiful agreement there. You can also use it to do what is called, Foucault state engineering. Basically, now you have electrons in a solid, periodic potential, but on top of that, you can put a field and you can dress your electrons with, the periodic potential coming from the field, and that generates again a different electronic structure, an electronic response, and that's basically a way of engineering your system optically. So that's also possible through these approaches. Finally, a lot of work has been put into light-induced superconductivity. Andrea Damascelli, Hamburg, has been championing this work. We've also done work in that direction. And the idea is to take superconductors and induce what is a transient superconducting state at much higher temperature, albeit for a short time, limited time. And so now the field is trying to push this into the nanosecond time scale by driving the system very, very strongly. The last point I'd like to mention, I think we are ready with this kind of technique to go into an approach where not only we photoemit a single electron through a process like this, but we actually photoemit a pair of electrons and detect simultaneously the pair of electrons. This is a project which has been recently funded. We're working on it right now. And the idea is, if I have a system where I have many body interaction and many body wave function, like for instance, Cooper pairs in a superconductor or pair states in a charge density wave system, when we remove a single electron, we lose any information about the inner structure of the wave function. However, if we can photoemit two electrons and detect them simultaneously in coincidence and look at the angular distribution, from that angular distribution of intensity, we can reconstruct the inner structure of a wave function and do real many-body spectroscopy, what we call, electron pair spectroscopy. So that is now what we're really working on, and I believe we really have a chance to get to, the more intrinsic many-body nature of these systems. With this, I'm coming to my conclusion. I've shown you what you can do by using time domain techniques in terms of learning and possibly driving system into new phases of matter. But I'd like to emphasize that this is part of a much bigger effort at the Quantum Matter Institute, which really revolves around the concept of quantum materials by design. And with this, I'd like to thank you all for your attention.